afternoon. This is Trudy Johnston from Material Matters. I'd like to welcome you to today's web seminar on the assessment of high-quality biosolids-derived products. You've joined today's presentation listening through your computer speaker system by default. If you'd prefer to listen through your telephone, locate the audio box in the web controls and select Use Telephone. The dial-in information and access code will then pop up. Throughout this seminar, you can send in questions for speakers by typing your questions into the questions pane and clicking Send. We will hold all questions until after the presentation during the Q&A session. Today's speakers include Robin Brandt, Chip Elliott, Malcolm Taylor, and Ludwig Zurich. Robin Brandt is a senior lecturer with the Penn State Department of Ag and Biological Engineering. Much of his research over the last 10 years has focused on sensory quantification of nuisance odors, including wastewater treatment plant emissions, biosolids in livestock, manures. He is a registered professional engineer with over 30 years' experience and serves as the director of the Penn State Odor Assessment Laboratory. Herschel Elliott, Chip, we call him, is a professor of ag and bioengineering at Penn State University for over 30 years. Chip has been involved in teaching, researching, and consulting in the air fate and transport of pollutants in aquatic and soil systems and the evaluation and design of land-based recycling systems. He is actively engaged in national debate on land-based recycling of biosolids and assists regulatory agencies nationally and internationally in developing regulatory policies for land application of biosolids and water treatment residuals. Dr. Malcolm Taylor works as a researcher and instructor at Penn State and serves as a research associate to Material Matters. His research has led to development of an innovative treatment technique for fixation of soluble phosphorus in biosolids using water treatment residuals as a binding agent. He has spent over 10 years as a consulting engineer working on a variety of biosolids and wastewater treatment residuals related products. And finally, Ludwig Zurich. Dr. Zurich is a professor in the Department of Diagnostic Medicine and Pathobiology in the Department of Entomology at Kansas State University. His research program in his laboratory focuses on ecology of foodborne pathogens in agricultural and urban environments, gastrointestinal microbial ecology of insects, role of gut bacterial communities in development of immunity, and vector capacity for human and animal parasites and pathogens, and development of novel microbiology-based strategies for insect pest management. Just general information about the WE&RF Research Project. It's high-quality biosolids from wastewater. I'm Trudy Johnston, the principal investigator, and we are working with Chris Piott, co-PI from DC Water. Our research project partners include Penn State University, Virginia Tech, Kansas State, University of Maryland, US EPA, and DC Metro COG. Our project's advisors include Jim Smith, formerly with EPA, Yan-Chi Chen with Penn State, and Ralph Eschborn from AECOM. The research was designed to encourage use of high-quality biosolids. To do that, we have to define high-quality biosolids if we plan to expand its use nationally. Part of that is also creating new products and demonstrating the efficacy of those new products. The focus is on using high-quality biosolids in urban and suburban settings, and how do we market that high-quality biosolids to customers? What role does social media play? What this webinar today will cover is our Task 1 research, which is assessing high-quality biosolids. Odor characterization of biosolids products will be our first presentation. Predicting biosolids odors from characterization parameters. Measuring respiratory activity with oxytop as stability indicator. And finally, characterizing biosolids vector traction by fly oviposition and larval development, and be followed by questions. Nuisance odor is a challenge, and the goal of our Task 1 team is to identify a surrogate parameter or series of parameters that will directly correlate to defining stability in biosolids. The treatment technologies in biosolids products that were represented through this research were 18 utilities from across the US and Canada, and even a product that was shipped to us from Australia. 17 of the 18 products were Class A EQ. One product was a Class B cake. The samples were all defined as customer ready, meaning that they were ready to be distributed to their final customer. Digestion technologies were meant to cover commonly used technologies across the US, ATAD, CAMB, flow through thermophilic digestion, pasteurization, and chemical oxidation. Customer-ready biosolids types, we had 11 cake products. 4 of those products were blended with other residuals such as sawdust, bark, or perhaps soil, and 3 thermally dried products using a combination of different drying and or dewatering methods, belt presses and screw press, centrifuge, and then thermally dried. And with that, we'll move to our first presentation, which is Dr. Robin Brandt with Penn State talking about odor characterization of biosolids products.
Well, thank you, Trudy. As we move forward here, I think it's probably appropriate for us to define what is a nuisance odor. So with that, whoop. Get rid of that. X that. Just use the arrow. Just hit it once. Oh my goodness. I have to get over onto that thing. Where? There, now try it. Now try it. Okay. So what is a nuisance odor? Well, there are several characteristics that one can use to define what is a nuisance odor. Frequency, intensity, duration, character, and hedonic tone. Frequency and intensity here are not really highlighted because these aren't things that we can control and measure on this end, but we can, in an odor assessment laboratory, measure intensity. We can quantify or characterize character, what an odor smells like, and hedonic tone, the pleasantness of a particular odor. Given this definition of nuisance odor, I want now to move forward with a little video here that is going to walk you through the process that we used here at the Penn State Odor Assessment Lab. While this is playing, I'm going to go ahead and talk through this. There's no video associated with the audio associated with the video, so I'll just go ahead and talk through here. So samples are received at the Penn State lab here, typically on Monday or Tuesday of a sampling week or an analysis week. Here Dr. Mike Heil is taking a sample that has been pre-prepared, left out to assume ambient temperature, broken up into smaller particles so we don't have any large clumps in here. And we try to get the size of the particles here to about 1/4 inch or less. he's placing these samples, or this sample, into a 3.8 liter jar. All of the parts of the system here that have any contact with the odor are either going to be glass, Teflon tubing, or Teflon lined materials, or stainless steel. Mike has placed the sample here in a water bath. The water bath is kept at 20 degrees C. So we place the samples into the water bath. They remain there in the water bath for a couple hours, so everything is kind of equilibrated to that temperature. Mike now is going to turn on the pump system here and start to flush 2 liters per minute of sweep air through each of these jars. Once we have swept the air through the airspace, the headspace in each jar, to the tune of 3 to 5 air exchanges, or maybe even more, we then are ready to pull samples. And what we're looking at here are the system that directs the air into the bottles. Mike is now taking the exhaust tube, which at the moment has been exhausted outside of the room, putting on a new Teflon tube, and then he's going to connect 10-liter Teflon bags. These bags are, they're really quite expensive and unique, but the reason for using Teflon bags is the odor doesn't tend to stick to the inside of the bag or leave the bag. The longer an odor sample is in a bag, the more chance there is that that odor may deteriorate or bleed out. So we use kind of top-of-the-line bags here. Mike has filled the bag to the tune of about 25%, 30%. He then takes the bag off of the system and squeezes the air out of the bag, then reconnects it back to the system, and now we fill that sample bag for the actual sampling. So here we can see 4 bags that have been filled. He's going to disconnect these bags, make sure the valves are all closed, and take all these bags and place them into an opaque garbage bag, basically, to protect these from any sunlight. So there may be, could be deterioration due to sunlight. He's now taking it into the dynamic olfactometer room. So you can see he's pulling a bag, sample bag. He's going to place this 10-liter bag inside of this dynamic olfactometer, which is a dilution device that allows us to dilute odor samples up to 60,000 times. He's now purging the system, priming the system, getting it ready for the first odor assessor now. So the first odor assessor is going to come in here. Each of these assessors has been qualified. These are experienced folks. They've been doing this for quite a while. And they all have a sense of smell in a very specific range. This assessor now is placing his nose piece onto the dynamic olfactometer, and when he pushes this button, where his hand is at right here, there's a 3-second burst of air, and that air will contain, in some samples it will contain the odor, in other samples it will not. This is a triangular forced choice technique. Only 1 of 3 of the exposures to the air actually has a sample in it. We have 5 people composing the odor panel. Each of those 5 people evaluates each bag 5 times. Once we're done with a particular bag, a sample bag, it's taken over into our odor quality lab. In this lab, we're connecting the remainder of that sample to a little device or glass fitting here that's actually a syringe body, where we can push on the bag and exhaust part of the sample out for the assessor to evaluate. Here he's taking a look at or comparing the odor that he just smelled to some dilutions of butyl alcohol. One of the odor intensity techniques that we use is to compare the odor strength to a known odor strength. These bottles contain known concentrations, again, of butyl alcohol going from basically just distilled water, that's our control, on up to 20,000 parts per million. This shows the sheets that each assessor fills out. On the left-hand side, this is for odor intensity. Each assessor samples the odor using the pillow test that we just looked at, and actually indicates on this scale here what that person feels is the strength of that odor, whether it be strong, very strong, whatever. There can be, we have assigned values. There's values that we can associate with their marks, and we can take those, each assessor does this 2 times, so we can take those 10 observations and determine a mean, a standard deviation, and so forth. This is one technique that we use for evaluating odor strength or intensity. The second technique pertains to those butyl alcohol sample bottles that we saw previously in the video. Each of these bottles, it goes from 0, again, the 0 concentration of butyl alcohol, up to 20,000 parts per million here. And the assessor again will say, sniff the odor and say the strength of that odor was similar to bottle 4 or bottle 7. This is considered to be a more objective technique. Each assessor also rates each odor with respect to pleasantness. In the middle here, the person really has no particular opinion regarding pleasantness. We move to the right. These are pleasant odors, going up to the most pleasant odor a person might experience. And on the left-hand side, we go on the negative side. This is unpleasant. Most of the odor strengths that we, or pleasantness scale values that we got during this assessment to date has been in the area of 0, maybe plus 0.5, out to about -5. We also look at odor quality or characteristics, and we ask the assessor to define as best they can what does this odor smell like. We ask each assessor to select up to 5 categories here from this odor wheel. This particular odor wheel is a modified wastewater odor wheel. Differs from the environmental odor wheel that we've used in other projects in the past. This is specifically for wastewater treatment facilities and biosolids. So here we're looking at this labeled magnitude scale odor intensity. I'm just going to note a couple things here. This is the scale that uses actually descriptors, where the people are indicating a descriptor describing just how strong that odor is. So with these descriptors, and these descriptors are associated with certain values on the scale. Down here below, around 6, a value of 6 on the labeled magnitude scale would be a barely detectable odor. On up to, say, 18 is a weak odor, between 18 and 36 a moderate, and so forth. And as we look at this, this is all of the samples that we evaluated in the lab for phase 1 of the project. And you can see there's a set of 3 observations for most of these. I just want to draw attention to a couple things here. One, background. This is a sample of an evaluation of the odor in the Teflon bag. We always look at the control. So we can see there's virtually nothing in the background there, so that's great. Note right here, let's see, sample 1A is a material that is anaerobically digested, and we can see that of the 3 observations, 2 of them are in the moderate range, and realize that each one of these bars represents 10 observations. So there's 10 observations in each of these bars. This very same material blended with some organic materials and stored for 2 weeks to a couple months is sample 18A. So it's the very same sample from here to here. This is really interesting. Continuing on. This is hedonic tone. This is the pleasantness scale. The more negative we go down, the longer these bars are moving, in a down direction here, is more unpleasant. So let's just take a look at that sample 1A again here. So here's sample 1A through 3 observations. Sample 18A is that same material that has been mixed with an organic material when stored 2 weeks to 2.5 months. Huge difference here. That's pretty compelling. I'll just note again that the background values here in each of these rounds is still essentially 0. Here we're looking at one of the sheets, the data sheets that's used with the dynamic olfactometer. As we look at this, you can see these 6s right here. These 6s represent correct detection levels for that particular assessor. Each of the assessor has been assigned a code, so we really don't know, who the people are. And these 6s, again, represent correct detections. It's either not always the same, even the same person doesn't always hit exactly the same mark. But this is all done blind, so the assessors don't know what they did the previous round. Now that's our manual maintenance of manual data. We also have this all on a computer with the dynamic olfactometer. As I wrap up here, I thought it'd be interesting to take a look at the olfactometer rankings of odor detection threshold. And let me see here. Here's 18A, sample 18A. We've been comparing 18A with 1A. And here's 1A. This is a material that has been anaerobically digested. And then later, after mixing with organic materials and allowing that material to wait 2 weeks to 2.5 months, we can see a dramatic drop in odor detection threshold. So with that, I will turn this over now to Dr. Elliott.
Okay, you've seen the extensive effort required to quantify the odors, and then, as Trudy had mentioned, one of our overall tasks was to identify surrogate parameters that would be directly related to the odor potential. So, in a sense, we were looking at these various correlations, and our response variable, it would be the odor detection threshold, the odor DT, as I'll call it, which you just saw on the last slide that Robin Brandt presented. Then our predictive or predictor parameters, we have ones that are routinely measured, for example, percent solids, total volatile solids, and then various constituents. Sulfur, iron, aluminum, ammonium, nitrogen, etc. We also had 2, I'll call them project-specific parameters. Methionine, the methionine content. Methionine is a sulfur-containing amino acid, and then respiratory activity. These are just based on some past research studies which suggest that these are, in fact, metrics that can be used to be related to odors anyway. We also had what I'll call discrete parameters, the age of the material, the digestion method, dewatering method. Discrete in the sense that they're not continuous, that is, we just basically put a value for different, for example, there's the dewatering method. We would just say, for example, call if the material 1, if it was centrifuge, 2, belt press, or 3, heat dryer. So that's what I mean by a discrete parameter. 2 types of data analysis that we're engaged in. One I'll just call bivariant. That's kind of one variable at a time. And how is that? Is the DT, the detection threshold, a function in any logical way or consistent way to a particular parameter X? So that's really what I'm going to report on mostly today, although some of the things I'll show you are going to suggest that perhaps a single parameter is not going to be adequate if we really want to develop some kind of correlation to odor DT. So a multivariate analysis, effectively we're saying that the detection threshold is a function of many parameters, the X values. So this would be the ith material is a function, the detection threshold for the ith material is a function of multiple parameters. And then these correlation coefficients basically reflect the strength of those individual predictive parameters. And ultimately we would hope then to find which parameters explain a significant amount of the variation in the dependent variable, that is the odor DT. First, perhaps I'll show you what appears to be a poorly correlated parameter. That is the data. This is ammonium nitrogen, the odor DT on the y-axis as a function of the biosolids material ammonium and nitrogen concentration in percentage. And you can see that their values, they're widely scattered, and the values down here, the low values would be sort of our low, and then we have this intermediate, and then we have high odor potential. And noteworthy would be, for example, here's a material which had no measurable ammonium nitrogen, but had a medium to high odor DT. And so one reason why this is perhaps poorly correlated is the fact that biosolids odors are not limited to, obviously, to nitrogen-containing odorants, but the sulfur-containing compounds and volatile fatty acids also play an important role. This is the odor DT as a function of total volatile solids, and it seems to be one that there is some correlation or some trends that seems to make sense. Obviously, here, if you have low total volatile solids, it really means you're going to have low odors. But then when you have higher total volatile solids, obviously the data can be scattered, but there is that upward trend as we would predict. Perhaps noteworthy here to show some of the variability, we have two products with the identical total volatile solids, 63%, pretty typical for biosolids materials, but they're at the odor extremes, and so it kind of shows the complexity of trying to sort out the data and find individual parameters that are going to explain all the variation. But it's noteworthy, these two materials, if we would say look at the odor DT as a function of the total iron content, they happen to have a very different iron content. And so the higher, and iron is probably one, since we use iron, various iron chemicals for odor control, we might expect that as the total iron content goes up, the odor goes down. And that's the general trend. However, you can see obviously there are many materials with effectively the identical iron content, but having very different odor detection thresholds. Some materials actually, because of the way they're treated, they tend to dilute constituent levels. Those materials, one is a lime stabilized material and the other is a blended product, so when you're putting other materials in there, you're obviously diluting maybe the potential for odor, but also those various constituents. So it just kind of indicates some confounding issues when we're trying to look at the data as a whole. Sulfur content, obviously sulfur is an important odor parameter, and so obviously the R squared for that is not particularly high. We have these three data points out here that are kind of the tail wagging the dog in a sense when you're doing a regression equation. But in general, we would expect that as the sulfur content of the material goes up, the odor would go up as well. Again, to show sort of the interaction of variables themselves, these three data points out here with high total sulfur also have high iron content. So the iron being, as I said, we do add iron for odor control. So it just shows the interaction of some of these parameters. And when we start going further on in our regression analysis, we're going to have to include not only individual terms for the parameters, but interaction terms. Okay, methionine. A past, actually, WE&RF-sponsored research project identified methionine, sulfur-containing amino acid, as important for odor, for predicting the odors in biosolids materials, and basically because it degrades to form methyl mercaptan, which is really a nasty, pungent, volatile compound. Actually pretty similar to ethyl mercaptan that gets added for natural gas and propane, so we know we have a gas leak. So you can imagine what that material smells like. So we were somewhat disappointed, I guess, in the sense that there wasn't maybe a stronger or better correlation. Again, we have a lot of scatter. We probably suspect that, one, there's some issues with some components of some of the materials that might actually cause an interference in the testing procedure, as well as many of the processes that we feel anyway that methionine is perhaps not as good as we had hoped it would be. I mentioned the discrete parameters, and here's just an example of the dewatering method where we just give a material 1 if it's centrifuge, 2 if it's pressed, belt pressed, and 3 if it's heat dried. And these are just kind of a box plots that show the data, and the data points are really outliers in the sense that they're beyond 1.5 times the, in this case, the upper quartile range. The box represents 50% of the data points. But again, we don't have, we have like 18 materials or so, but at least it tends to, the dark bar, by the way, is the median value. And so it tends to confirm the general belief that centrifuge materials tend to be more odorous, largely because of the high shear associated with centrifugation that tends to release biodegradable proteins into the solution. And we only had, I think, well, 3 or 4 materials that are heat dried, but perhaps the median odor for those materials tends to be higher than the belt pressed materials. So we can't state with assurance, but we can say that, say, drying a material or pelletization won't automatically result in a lower odor material. The other one of our project-specific parameters was this oxytop respiratory activity, and it's somewhat similar to, say, almost a BOD test, and Malcolm Taylor is going to discuss that in more detail. But again, we have widely varying values, and perhaps the feeling is that some of the processes have a differential effect on the microbial population and processes, and that's a reason for some of the scatter. At this point, we tend to conclude that maybe the oxytop as a single parameter might not be very reliable for inter-product comparisons, but it may be useful for gauging the time-dependent odor changes in a given biosolids product, and Malcolm Taylor is going to talk more about that. But before I turn it over to Malcolm, I just wanted to show where we are going with the data analysis. Hopefully through the multivariate regression analysis, we're going to identify the predictor variables that are most important in explaining the variation in the odor detection threshold. Ultimately, we hope to define some thresholds for these critical parameters below which we can sort of have a reasonable assurance that the material would be considered high quality from an odor producing perspective. I'm going to turn it over now to Malcolm.
Okay, everybody enjoying the fantastic presentation so far, and we'll jump right into it. And so I'm going to basically review oxytop, assuming that most of you aren't familiar with that. I'll give you a background as to what it is, discuss the challenges, interpreting the results, evaluate it as a method for measuring stability, and discuss our ongoing and future efforts. And so oxytop, think of it, the most straightforward way to think of it is like a BOD test for solids, in which the biosolids are put into a vessel and allowed the respiratory activity of the sample is measured. This is done by measuring the consumption of oxygen. As the microorganisms in the sample consume oxygen, they respire carbon dioxide. and we avoid a buildup of carbon dioxide by precipitating that out with sodium hydroxide. And so the idea here is that the off gases are effectively turned to water, and so the drop in pressure, the drop in oxygen in the vessel, is correlated with the respiratory activity of the sample. The other parameters in this equation here are simply the molar volume of oxygen, standard temperature and gas constants, and the mass of the sample. Similar to BOD, the RA4, you'll see this throughout the slide, it's really nothing more than the respiratory activity at day 4 or 96 hours. I'm not exactly sure what the purpose of selecting 4 as opposed to 5 is, but that's the standard that you'll see in the literature. The 96-hour, at that point, what is the accumulative respiratory activity? And so with that defined, you'll see that throughout the presentation. So I have a little video for you here. We'll just sort of walk you through this. For those of you that haven't seen this before, Oxytop system is made in Germany. Here we have the sample in the same tubs. This is the same sample that was used for the odor panel, so they're exposed to the exact same conditions. They've been aerated, equilibrated in atmospheric conditions for about 2 hours to just kind of come to room temperature. And again, that's a subsample of that sample that was used for the odor. Here's the sodium hydroxide pellets that will react with any carbon dioxide produced and effectively turn to water. And so here we are. It's the sodium hydroxide is put into this little cage, which is then secured on the top of the bottle, and the remote starter then effectively starts the test, and that sensor on the top of the bottle there that you see blinking is effectively now a pressure gauge, and it's gonna record the pressure in the vessel over the next 4 days. Here we are putting the sample into an incubator at 20 degrees C to control the effect of temperature on the pressure. And so that's it. The intention of that video is to sort of illustrate that it is pretty straightforward. Here's another sort of example. So after 4 days, we come back and we get the sample out of the incubator, and this is what you'll see. So effectively, over time, the pressure drops, indicating a consumption of oxygen, and this is the type of curve that the equipment will generate for you. And so using that equation that I showed you previously, with pressure as the master variable, you calculate the respiratory activity of a material on milligrams of oxygen per gram of dried material. And so here's a typical curve that you might see. Simply read, at 96 hours, the respiratory activity in this instance is 36 milligrams of oxygen. So what does that mean? Well, most of the literature, a lot of the most common use of this system has been in Europe, and Austria has an ordinance that suggests that if a material is greater than 7 milligrams per liter of oxygen, you're not to put it in a landfill. In other words, it has some biological value to it. It might be used in a resource recovery facility, or there's no sense in putting biologically active material in a landfill. And so this is sort of a cutoff of an inert material. And so this was our starting point to see kind of where we were at, where biosolids fell on the scale, because to our knowledge, there has not been a comprehensive evaluation of biosolids using respiratory activity as a parameter. Based on that, I set out to say, okay, well, what, dirt from the backyard or maybe mulch, what kind of respiratory activity would we have? And so I effectively followed the same protocol: 2 hours in a tub at room temperature, allow it to equilibrate with ambient air, started the test, and as you might expect, the respiratory activity of dirt is effectively nothing, and the aged mulch, very small amount of respiratory activity. In other words, both of these materials would be suitable to be put in a landfill. They're effectively inert. And there you go, about 2 milligrams per of oxygen for the mulch. Next thing I did was run the same test on household compost feedstock. Basically all the lemon peels and whatnot from the compost, and some fresh cow manure from a local dairy barn. And again, as we might expect, the respiratory activity for these materials is significantly higher, 120 or 105, certainly not suitable for a landfill, very unstable. A lot of biological activity remains before they become stable, which is, again, what you would expect. One of the things that we noticed about the OxyTop was we were able to get some very strong repeatability and reproducibility, which was quite surprising to me. I thought there'd be a lot of variability in the results, but once we sort of got the protocol down, we were able to, we took the same sample, divided it into 4 subsamples, we were able to recreate these curves. And so we have quite a stringent QA/QC program in place that if any one of the samples derived by more than 15% from the others or from the average, that it was sort of dismissed as an outlier. Again, there's always sample non-homogeneous samples, or a rock or a pebble in one sample, or one sample's particularly not representative of the other. And so that was sort of a built-in QA/QC, but we were able to really hone this protocol in and feel quite strongly that we're getting good results. So the curves that you see in this presentation are the average of 4 replicates in all instances. Now, having said that, there are some hiccups that we ran into, and so we're effectively going to develop a protocol for this. And so here's an example of one of those hiccups where we see the pressure change for 2 samples, and you would expect here that the pressure change for the sample weighing 1.3 grams is a lot more than the smaller sample. So you might suggest, okay, more pressure drop, more respiratory activity. But when you express those results on a per dry mass basis, it's actually the smaller sample here that has a higher respiratory activity. And so what we suspect in this instance here is that the larger sample towards the end of the 4-day run is actually becoming limited with the available oxygen in the vessel, and so respiratory activity is slowed beyond optimal conditions because oxygen is becoming limited. Here's an example of that. Based on that finding, I sort of forced the function and put a lot too much sample in, and if you see here, replicate 1 and 3, about halfway through the test, respiratory activity all but ceased. And again, that's effectively because there was no more oxygen available for the respiration to continue. And so that's one of the things you need to be aware of when you run this test. Not only do you need to look at the final value, but you need to look at the shape of the curve to ensure that you're getting unencumbered activity throughout the 4 days. Another hiccup or sort of protocol issue that users need to be aware of is the temperature effect. So the measurement, the hectopascal is 69 of those is 1 psi, so it's very precise. And so if you have the samples at room temperature and the bottles at room temperature, and then you put them into an incubator at 20 degrees C, you're going to get a quick change in temperature, which is going to cause a quick change in pressure, which is going to be reflected in the results. And so steps need to be taken to put the bottles in the incubator ahead of time to allow the whole system to stabilize. And so again, it's a very sensitive measure of pressure, and temperature and pressure are obviously very strongly correlated with one another. Another potential thing that we need to be aware of is a lag time. This is an example of where we had a dried product. It was dried to 97% solids using a thermal dryer. Effectively no moisture or water required for the microbes to do their thing. And so understanding that, we needed to promote conditions conducive to respiratory activity, and so we wet the samples to 60% solids. But even in that instance, it took the bugs about two or 3 days, 60 hours until they actually started respiring. And so for those samples that we needed to sort of kickstart, we needed to be aware that we weren't going to measure their respiratory activity until after that lag phase was over. Another example is the sample that we had that was lime stabilized. It had a pH above 12, and in this instance, there was effectively no respiratory activity whatsoever. As you might imagine, at a high pH of 12, pretty much everything's dead and or dormant, and so we didn't see any respiratory activity for that. And so these are examples of learning curves associated with the test, and one of the things that we'll provide as part of this final report is effectively a standardized protocol that will highlight these things, so that if we do recommend users to use Oxytop, that you're aware of these potential stumbling blocks ahead of time and can sort of develop a usable standard protocol for your product. So as Dr. Elliott previously alluded to, biosolids display a wide range of respiratory activity. Here we have an anaerobically digested cake, respiratory activity of near 100, and it's in our high odor group. Here's an example of a heat-dried product, wet to 60% solids, very low respiratory activity. It also has a high odor. And so here's an example of where you can't say the lower the respiratory activity, the lower the odor. Again, a little bit unfortunate, but if we had a silver bullet, we'd be rich, and we wouldn't be here. And you saw this slide before, and so the scatter's all over the place. And so we say, well, that's really too bad, but as Dr. Elliott had previously referenced, there's more than any one variable affecting odor, and so the respiratory activity alone is not a predictor of odor, as we might have suspected. So the next kind of sort of, okay, well, what are we going to do? Would we just throw this out, or would dismiss it altogether, or what else can we do? We know that it's a good measure of stability. We know that the more stable the product, the lower the respiratory activity. So how can we correlate that with odors? And I'll explain that. So here's a study, or I'm sorry, a summary of what I've already shown you. And so the biosolids, most of the products were between 25 to 50, certainly not going into an Austrian landfill, but certainly not as active as fresh cow manure, as you might expect. Some of the highest were above 80, maybe as high as 90 milligrams per oxygen. And so again, we're investigating the differences in the individual samples as to were the samples anaerobically digested, were they digested by advanced stabilization methods, and what does that ultimately do to the respiratory activity, and that's part of our ongoing efforts. But ultimately what we're trying to do is to see if we can use respiratory activity as a surrogate indicator of odor. And so here's an example of where we have two products, a fresh cake right off of the belt filter press. It has a respiratory activity of about 60 milligrams per liter. And then we have the same product that has been cured. And by curing, it's not formally composted, but it's stored in windrows, periodically turned over and aerated, and effectively allowed to be cured, effectively dried for 45 days. In this instance, we found that the respiratory activity was dropped from 60 to about 10. When we compare that to our odor results, we do see that the values correlate. We cut the odor in about half. And so this is sort of something that we've sort of just really embarked on, but we're hoping that this tool might be useful in that if you were processing a material further and you set a benchmark for what your unconditioned or fresh material, what odors that you had, as the material aged or was processed or was blended, you might be able to use the oxytop as an indicator of how far along in the stabilization process you are and the associated reduction in odor. Here's another example of that. Here we have an aged blend. This was the product 1 and 18A that Dr. Brandt had previously referenced. But again, the fresh cake had a respiratory activity of 60, and the aged blend had a respiratory activity right around 7, very stable material. And again, the odor detection threshold was reduced from 1,000 to 341. And so these are an example of where we hope this might lead the use of our respiratory activity. At this preliminary stage, I might envision that similar to volatile solids reduction in a digester, that this would be your own sort of standard to your own product, so that if you were to get an odor panel done and you know that respiratory activity at a certain odor is a certain level, you sort of establish your own internal benchmarks, that once you have that information, you could then use respiratory activity to determine the relative reduction in odor without having to run, after 2 weeks of curing, run out and get an odor panel, and then 4 weeks of processing, run out and get another odor panel, that you might be able to use the respiratory activity and say, yeah, we can see that this product's getting more stable, and based on our previously established odor benchmarks, we're confident that we've reached the goal that we're trying to obtain. So that's where we're hoping this is going to go. Again, this is somewhat in the preliminary stages, but at the very least, this report will obviously share these results and provide information for utilities to look at, but also, as I mentioned, a detailed protocol of, if you are considering using this method of assessment, the things to look for and how to avoid stumbling blocks that will be useful for the industry in general. And so with that, I'll summarize quickly. The oxytop provides, it's very inexpensive. The entire system, as you saw in the videos, not many moving parts, $1,500 to $2,000, provides a reproducible measure of biosolids stability. As I mentioned, we're developing a standard operating procedure that would increase the value of the results. We don't see a direct correlation, but again, with the many number of things affecting odor, that's what we would expect. So we certainly don't see a direct correlation between respiratory activity and odor, although we have seen some trends. Those materials that have been stabilized by advanced stabilization appear to have lower respiratory activity and lower odor. So we're certainly going to iron some of those trends out. And as I mentioned, there appears to be potential for oxytop as a biosolids criterion, as a sort of relative to your own product. And so we'll sort of iron the rest of that stuff out as we move forward into the next phase. And so with that, I'm going to pass it on to our colleague. If he's here, can I go ahead and Ludic?
Yeah, I'm here.
So I think he has control.
All right. Can you hear me okay?
Yes, we can. Yes, we can hear you, Ludic.
All right.
Go ahead.
So here at K-State, we have been evaluating biosolids from different wastewater treatment plants for their attractiveness to insects, specifically houseflies, and also assessing if these biosolid products can actually serve as a sort of habitat or substrate for maggot development and potentially generate a large population of flies. So I'll just give you a short background on housefly biology. Housefly females basically lay eggs into suitable habitat for larvae, which are typically decaying organic substrates such as animal manure, garbage, or basically anything that is decaying organic, and it has a large microbial community. So these biosolid products are potentially attractive for flies and can potentially serve as a habitat for development of maggots. So flies lay eggs into those habitats. The eggs hatch in about 1 day and become maggots. And the larvae or maggots feed primarily on microbes in that habitat, grow bigger, molt a few times, then become pupae. And a pupa after about a week becomes a flying adult again. So the whole life cycle typically in nature takes about 2 to 3 weeks. So for everybody knows that house flies are major nuisance. A single house fly can be really annoying, and beyond this nuisance issue, flies, because they develop in decaying organic substrates, are just loaded by all kinds of microbes, and they have been shown to transmit all kinds of microbes that originate from manure and other decaying substrates. And some of these microbes are potentially zoonotic and foodborne pathogens for people as well. So to assess how attractive these biosolid products are for flies, we basically we got substrates from 8 different wastewater treatment facilities. Our positive control was fresh dairy cattle manure. So we basically placed 50 grams of each substrate into a sterile petri dish, and then we ran bioassays as a two-choice assays. It was always one biosolid substrate against the cattle manure. This was done in plastic cages that were placed into a wind tunnel. I'll show you pictures of that shortly. And for houseflies, we used the lab colony here from K-State. We selected randomly 20 females that were ready to lay eggs, and these were placed into those cages for 24 hours. After 24 hours, we took these petri dishes out and basically counted number of eggs that were laid into each petri dish. And this was basically used for assessment how attractive these biosolids products were comparing to cattle manure. So here is a picture of how it looks. On the left side here, this is fresh dairy cattle manure, and in the middle and on the right side, these are 2 different biosolids from wastewater treatment plant. So these were placed into a cage. So this is one choice, this is a second choice here. And these cages were then placed into this large wind tunnel. It's called a wind tunnel because this fan actually generates a fan or sucks the air out of that cage. So there is a supply of fresh air so it doesn't get saturated by odors from these different substrates here. Here is another angle of that cage again. So here are some preliminary data that we got. On the x-axis, there are different substrates, biosolid substrates and cattle manure. The cattle manure is in blue bar, biosolid is in red bar, and on y-axis, it's a percentage of eggs that were basically recovered from each dish. So you can see quite easily that these substrates DO1, FO3, and FO7 this is where the biosolid substrate was much more attractive than cattle manure, especially this FO7. All 100% of eggs were found just in the dish with the biosolid substrate. And there was another substrate, E10, that sort of was also attractive, but not as attractive as cattle manure. About 65% of eggs were in the manure, and the rest was in the biosolid. And the ones where you see only blue bars, these are biosolid substrates where we didn't recover any eggs, and all eggs were found just in in the cattle manure, 100% X were in the cattle manure. So this is how we assessed how attractive different biosolid substrates are comparing to cattle manure based on number of eggs that were laid on each dish. The second part of this study was assess if these biosolid substrates can actually serve as a habitat for housefly maggots if the flies were attracted there and laid eggs. So again, we placed 50 grams of each substrate into sterile petri dish, and our positive control was fresh cattle manure. And in this case, we artificially placed 20 freshly laid housefly eggs on each dish, each substrate, and then basically placed it into these small cages with openings, and basically waited for eggs to hatch, maggots to develop into pupae. Typically, the last instar larva crawled out of that dish in the container, pupated, and then we basically counted number of adult flies once they were produced from each pupa. And here is the data. So the C is the control, the cattle manure, and here are different biosolid substrates. And this is showing percent development of houseflies from basically 20 eggs that reached adult stage. So in the positive control, the successful development ranged from about only 35% in this bioassay all the way to 75% in this bioassay. And this is most likely due to differences in the fresh dairy cattle manure that we were collecting over time from K-State farm. What's important here is that none of the biosolid substrates actually produced any adult flies, with this exception of the substrate DO1 that was actually quite successful and produced 70% of those eggs developed all the way to adult flies. So in sort of preliminary conclusions, this is all based on just one replicate of these assays. There are some biosolid substrates such as DO1, FO3, and FO7 that seem to be more attractive to housefly females than the fresh dairy cattle manure. On the other hand, there are other substrates that are not attractive at all. So they do clearly differ in terms of how much they attract insects, primarily houseflies. And as far as the maggot development, there was only one substrate, DO1, that supported housefly development from eggs all the way to adult stage. So you can see it is DO1. I don't know which biosolid substrate it is, what process was used in this wastewater treatment facility, but this one does seem to be not only attractive for houseflies for laying eggs, but the eggs actually do hatch and develop all the way to adult flies. So this obviously needs to be replicated, and we are actually currently in running bioassays in the third replicate. So we'll see how accurate and how much it actually can be replicated and how much it holds water overall. And this is it from K-State.
All right, thank you, Ludik. Since it's just after 2 o'clock, we have plenty of time for questions. And right now, if you can use the question pane in your web controls on the right side of your screen to ask our presenters questions. Simply type in your question and click send. And we'll give you a few minutes to do that. I'll direct those questions and ask those questions of our presenters today. And perhaps to get started, since I don't see any questions right now, I will ask a question for Penn State. You indicated that percent aluminum is one of the variables you investigated. Was there any strong correlation between odor detection threshold and the biosolids aluminum content?
We were aware of previous research by John Novak and colleagues that's shown that when alum is used in dewatering, it tends to reduce the biosolids odor, ostensibly because the aluminum strongly binds the labile proteins and thereby limiting their availability for microbial breakdown. When we looked at all the materials, when we plotted odor DT versus, say, the total aluminum concentration, we got a very poor correlation. In fact, the R-squared was 0.0174, so it was almost flatlined. However, again, that includes all the materials, and I don't know how many of them are actually using, say, alum for dewatering, but there are many materials. I usually look at, say, 1% aluminum as maybe typical for plants that aren't adding it intentionally. So we have a lot of our data points down there, and then we have some sort of scattered points for higher aluminum concentrations. Does seem to be maybe an interaction with iron when we have iron and aluminum together. There was materials with lower iron, say for a given aluminum concentration, tended to have higher odors. But again, it's something we're going to have to sort out by looking at the detail, the data in more detail, and perhaps trying to determine, say, what are the interactions between various parameters.
All right, thank you, Chip. There seem to be quite a few questions about fly attractiveness, and I guess since Ludic doesn't know what sample DO1 was, most of the samples that came into Ludic for the Kansas State were blind samples. So maybe I'll ask Penn State to answer this question. Everybody's interested in the type of processing and dewatering that represented that sample DO1. And Malcolm, maybe you're the one that can answer that question.
Okay. What we have on that is anaerobically digested, the technology dual digestion, dewatering with a screw press, and 24% total solids, 60% total volatile solids. And we described it as a moist, clumpy cake. It was taken directly from the press.
And I guess I might follow up asking the question in terms of taking Ludic's data that he presented today, how does that get incorporated then into the Penn State statistical analysis?
Yeah. By the way, that's sample 1A that Robin Brandt was mentioning. So there'll be a reference back to those odor DT values.
Yeah, 1A, and by the way, 1A was the sample that had the higher, or say the more unpleasant odor, the higher intensity, and the higher DT. So it kind of fits nicely with what Ludic found, with respect to the flies.
Okay, we have a question also about the biosolids treatment processes behind the 3 samples that attracted the flies, and I don't recall what those numbers were for those samples. So Ludic, if you could just mention those other 3 sample numbers too, then somebody at Penn State can describe what those what technologies those samples represented.
Well, can you go back to my previous slide, the last before last? For the summary, it shows. I don't remember it from top of my head here.
No, but I can look at it on another slide set that I have here. So let's see. It was sample 01, 03, and 07.
Can you, am I audible?
Yeah. Yes,
All right.
you are.
Okay, so we already talked about sample 1. That is a anaerobically digested cake. Consider the digestion conventional digestion, I guess you might say. In a similar fashion, 5B, anaerobic digestion, dewatered with a centrifuge. That actually, of the 18 samples, we had indicated at the start of the presentation that one of the 18 was a Class B. So not coincidentally, maybe, that is a Class B product. So there's that. But again, I consider that a conventionally anaerobically digested material. And product number 3 is heat dried to 97% solids, but it's an undigested material. And so there's definitely some valuable insight there. One caveat I must bring up to light is that for that material that was 97% solids, before the fly test was done and before the odor test was done, moisture was added to that sample to simulate conditions that may be observed in the field when a dried material is added to soil and the ambient soil moisture and or rain is mixed, and the odorous, the activity of the dried material sort of kicks in. And so it should be noted that material was intentionally wetted prior to these measurements. But the fact that it was an undigested material certainly provides some valuable insight.
And sample 07?
Now that's, I thought, I'm sorry, I thought I already described that. That was the second one I discussed.
Okay. We have a question here of the samples 1A and 18 that were the same anaerobically digested biosolids. What was the organic material that was mixed with 18? I'm not sure we have that information. Perhaps we do.
What I have here, Trudy, this is Robin, is finely graded mulchy mix. That's all that I have.
Okay, so it would have been a sawdust or maybe wood chips?
Yes. Leaf litter. It's a combination of woody debris, leaf litter. Think of it as yard compost and finely graded woody waste.
Okay. I have a question here. I don't see any other questions on our question pane. If anybody would like to add questions, please do so. But I have a question about thermally dried products. And do the results show that thermally dried biosolids have lower odors than other types of biosolids? And as you mentioned, Malcolm, what about re-wetting?
All right, so the answer to your question is no. Thermally drying in and of itself is not shown to reduce odors significantly below other products. Again, as I alluded to before, all the data that you saw today was on samples that had been, dried samples that had been re-wet, or think of it as activated. The reason that was done was, particularly for the flies and for the respiratory activity, we needed to have a situation that was conducive to biological activity. As to not sort of point out dried products as the bad guys, part of our ongoing phase 2 efforts are to measure the odor of the dried products as is, as in dried. And so that'll sort of be some of our forthcoming conclusions as to what's the difference between the dried product in a dry form versus in a wet. But in summary, no, drying in and of itself did not reduce the odors significantly below that of the other products.
Trudy, I might add as well that if you look at the chart, the last chart that I presented showing ranking biosolids from a low DT to medium to high DT, the facilities on the extreme right of that chart are, I think 3 of those are dried materials that have been wetted. So they were among the most odorous. Yeah, right in there.
You mentioned that last slide of yours that actually ranked all the products according to odor, DT, is there any comment that you can make about how we saw some grouped in the low odor group, some in the medium odor group, and then some of those in the high odor group? I know you haven't done your full statistical analysis yet, but are there any general comments that you could make about your final determination?
I can mention that the low odor group materials were materials that, and there were only a couple, but were materials that had been aged and mixed with organic, some organic material, or mixed with organic material and aged. On the extreme right-hand side, the most odorous, again, the thing that stuck out to me was it was largely comprised of the heat-dried materials. Another thing I might note about that chart is you see, in most cases, we had 3 reps for each of these materials, and the reps were separated by a period of time. Were sent in, maybe several weeks after, and each time we wanted to see another fresh sample. But I'm not sure that we really got exactly what we wanted in all cases, because we did see some variations in DT levels here that I can't explain in the lab, because in the lab we basically had the same, for the most part, the same 5 odor assessors the whole way through. From the perspective of QA/QC, it really worked out beautifully here, because we have a very committed group of folks that really got into this. We had these odor panels run in the evenings, and these folks would come in and spend their evening with us to take care of their observations and head home then. So I can't explain the large variations, some of the large variations among the reps, the 3 reps. And at this point, my explanation is that we got materials that weren't quite the same from each rep, or something happened at the sample taking end.
I guess to add on to that, Robin, the way these samples were collected, it was 3 discrete samples collected about a month to 6 weeks apart. It could represent variable quality that's coming from or processing or other processing upsets at a wastewater treatment plant. But we were looking for getting very similar samples and looking at could we replicate those same results. So the fact that we can't replicate them may indicate, and Robin, you can speak to this, may indicate that the quality of the product that we got was different with each sample that we got.
It could be, Trudy, that sample 1 was taken from a pile and sample 2 was taken from another pile, or maybe the same pile. And so that such that the big difference could be really age, perhaps, the same material but aged. Or maybe the ones that were really high were maybe straight off belt filter press. We don't quite know right now. We have to explore that a little more. But this is the phase 1 group. We were trying to get a look at a number of different facilities and what kinds of variations we would see. The phase 2 group are being, I believe, a little more controlled and communicating more with the participating wastewater plants to see that we are getting basically the same kinds of samplings.
Okay, and just one other question sort of related to that is that I know that a question that came in the research early was, how do we handle storage? Because we know that so many biosolids products are stored, and we purposely did not consider storage, but I know that we've talked about it internally. Is that potential for, let's say, the next phase of this research, looking at storage and how that impacts odor quality?
One of the things I noted as I was talking about the odor DT levels was that samples that had been stored seemed to have lower DT levels. And what we were asking for was materials customer ready. So there are facilities that have storage built right into their program. And there was probably more often a number of facilities that were pulling samples right off of their belt filter press. So in effect, we have looked at some storage, but we don't know what happens with these particular facilities that were just pulling samples right off the belt filter press, or coming out of the centrifuge, put it that way. So that so far it looks like it could be an assistance in reducing odors. Storage isn't always possible for a lot of folks, but.
Okay, and I have a question about publication of the data. I know that our report is due somewhere here mid-year, our report to WE&RF, and I suspect that it will go through several reviews before it's published. I know that we will be presenting papers probably at our RBC conference in 2018 and West Tech 2018. So I will, if you can forward that question on to folks at WE&RF. I'm not sure exactly how it gets final published for subscribers. There was another question about odors from alkaline stabilized biosolids and comparing that to heat dried, and maybe Penn State, you can answer a few questions on alkaline stabilization and what you found.
I think, Trudy, we only had one material. Am I remember right? One material that was undigested, lime stabilized.
No.
No?
The one material we had lime stabilized was treated with a pasteurization process and then lime stabilized. And the odor of that material was
It's 13A.
was
I think that had about 50% lime. I know where that sample came from.
yeah.
Between 40 and 50% lime. So it was a very high limed product. And they don't have stabilization ahead of the pasteurization. So it's pasteurization in one unit followed by lime stabilization.
Yeah, and the odor of that product was on the low end compared to the other products. So, you know, it did well. It ranked well, comparatively speaking, to other products, if that was the question.
Right, and because we didn't really look at storage over time, we got the product probably ready for customer use, and the pH was still around 12. So there hadn't been any biological activity.
That's correct. And let's be clear, there are certainly some exceptions, but for the most part, the data that you saw today is of samples that had just come directly off of this, out of the centrifuge or off of the belt press. Certainly the ones that were blended, that sort of go into their own category, had a curing time, and we sort of tried to highlight those. But all the other samples were pretty much what would be dumping into the back of a truck and being hauled to the farm. And the pH of that material was 12.5.
Right, so it's got a considerable amount of lime in it.
Yes, it was heavily limed.
Okay.
But again, the odor of that product was relatively low. So from that perspective, you could suggest that that was an effective method of reducing odor.
And I think I have one final question here, and that has to do with the heat-dried materials. I believe there were 2 heat-dried products that were digested and one that was not digested or not stabilized in any way before drying. Did you see much of a difference between the thermally dried products?
Have to look them up here, Trudy. 3A versus 11A. 15A.
Not really. I mean, they're kind of all they're all, like Robin alluded to earlier, not a whole lot of variability among the three samples.
So 3A versus 11A versus 15A and 17B.
Not 17, 15. Oh, that was a solar drive product.
Okay.
The evidence doesn't show that there's a large difference between digested and thermally dried versus undigested and thermally dried, or is that something that we will discover once you do your more thorough statistical review?
What you just said is correct. However, big asterisk next to that, we only had 3 heat-dried samples. So it's hard to conclude based on that small number. But yes, the undigested heat-dried material and the digested heat-dried material were comparable from an odor perspective. But again, it would be hard to pull too many inferences from such a limited sample size.
Okay, and our undigested heat-dried sample was the one that Ludic found that was most attractive for flies.
Yes, one of them, yes.
Okay.
After it was re-wet.
I don't see any additional questions popping up, so I would like to thank all our speakers today very much for presenting information on this research. And I would like to thank you, all the participants, for participating in today's web seminar. We would also like to let you know that you can contact the speakers directly. Their email address is on this final slide. So jot down that information if you're interested in contacting them directly. With that, this will end our webinar today. Thank you very much.